Hey folks, test 3 is now upon us, so here is what you need to know. Just like all the other tests, you'll have 90 minutes to do it, a full lab block. It'll consist of 15 multiple choice questions, those are 2 points each, a lab-based question, free response questions. Just like all the other tests, you are more than welcome to bring a cheat sheet, one piece of paper, 8.5 by 11, front and back, of any handwritten notes that you want to bring with you. Also, make sure that you bring a calculator that is not your phone, and let me know if you need to borrow one. I will set that up for you. So let's dive straight into some of the concepts that you'll need to know and be able to work with. We start by looking at energy. The unit of energy is the joule, and 1 joule is equivalent to a kilogram meter squared per second squared. And you can find that by plugging in the proper units to each of these variables. In each and every one of these equations, you'll always get back to kilogram meter squared per second squared, which is a joule. So each and every one of these has units of joules. That's the only reason you can add them together to find an object's total energy. So looking at these one at a time, the kinetic energy of any given object is 1/2 times its mass times its velocity squared. If the object is not moving, it has no kinetic energy. So if you've got something that's starting on a ramp from rest, you can say that the initial kinetic energy is 0. As soon as it has mass and velocity, it's got kinetic energy. The gravitational potential energy of an object at any moment in time is its mass times g, that's the acceleration due to gravity. On Earth, that's going to be 9.81 meters per second squared, multiplied by the height in meters. Then there's elastic potential energy. This is how much energy is stored in a stretched or compressed spring or rubber band or something like that. X is going to be the distance away from its rest position that it's stretched or compressed. So do note that X is not the length of the spring, it's simply the distance away from its rest position that it's stretched. Look at where it ended before, look at where it ends now, find the difference. That's your X value. K is what's known as the spring constant of the object. The spring constant is simply how many newtons of force it takes to stretch the thing 1 meter. In many systems, the total energy is going to be the same before and after. Ask yourself if something is coming in from outside of the system and pushing an object or pulling it or slapping it or whatever else. If not, the total energy will be the same before and after. Examples of this are some sort of roller coaster on a track where gravity is the only force bringing it downward. It's simply converting potential energy to kinetic energy. Or if something's sliding across a frictionless floor and it compresses a spring, then it's converting kinetic energy to elastic potential energy. Whenever you're faced with these conservation of energy problems, take all the different types of energy before and add them up, take all the different types of energy after and add them up, set the before and after conditions equal to each other, and you've got it. Now what happens if there is something coming in and messing it up? Rude. That's when work is done. Work is a change in an object's energy caused by this force reaching in, pushing it, pulling it, slapping it, kicking it, whatever else. And work is simply defined as the change in energy of the object. Now it'll be positive if energy is added to the object. If I lift something up, or if I shove something and it moves faster as a result, I've added energy to it, I've done positive work to it. If I take energy away, I lower something or I slow it down, I've done negative work on it, I've taken energy away from it. Work can also be found as force times distance times the cosine of theta, where d is the distance over which the force is acting. So if I run up and I shove a textbook away from you because you're working on history instead of physics, and I'm not cool with that, then d is only the distance over which I push it. It does not include the distance after my hand lets go. So it's the force I exert on it times the distance over which I push it times the cosine of theta. Theta is the difference between the force and distance vector. Well, that's work. If you take that work and divide it by time, you've got power. Power is measured in watts, and that can be confusing for a lot of people. This is not watts. This is work. So don't confuse the symbol W, which means work, versus the unit W, which means watts. It's kind of like how mass has a symbol m, but it's not measured in a meter. Work has the symbol W, but it's not measured in watts. It's the exact same thing. We talked a bit about Hooke's law. That's simply the force that it takes to stretch or compress a spring is equal to the spring constant times the distance away from the rest position that it's stretched or compressed. There's a little negative out front. That negative simply tells me if I pull a spring to the right, it'll have a restorative force to the left. Whew. That's a lot to take in all at once, so let's take a little break, take a look at a baby sloth. Aww. And now let's talk about momentum. Momentum is denoted by the symbol p, and it's simply the mass of an object times its velocity. Now, within a closed system, nothing reaching in and exerting a force from the outside, the total momentum of the system will always be conserved. That means when two objects collide, the sum of their momenta added together is going to be the same before and after the collision. There are a few different types. There's perfectly elastic, that's where they bounce off really nicely. And there's perfectly inelastic, that is where the two objects stick together. Most collisions are somewhere in between, where objects don't fully bounce off of each other, but they don't fully stick together. That's called inelastic. We didn't really do examples of that. Momentum is conserved there as well, but we mainly focused on perfectly elastic and perfectly inelastic collisions in class. When they're perfectly elastic, you've got conservation of momentum, where I just add up the momentum of each object before the collision, add up the momentum after, and you've got it. Now in this case, momentum is a vector, so make absolute certain that you include any negatives if an object is moving in the opposite direction of a different object. Now, not only that, for elastic collisions, kinetic energy is conserved. We didn't do many examples of this in class, but if you didn't know either of the final velocities of either object, you could use this to set up a two-equation, two-unknown system. I'm probably not going to ask you to do that for the very first time on a test. Just FYI. Now, for perfectly inelastic collisions, the two objects are stuck together, so their final velocity has to be the same. The conservation of momentum equation is exactly the same, but with the final velocities being identical, I can pull that out and just add the masses together. Impulse is a change in the object's momentum because of an external force. So just like work is a change in energy, impulse is a change in momentum. And you can find that by multiplying the force acted on an object times the amount of time that force is active. If you end up in a situation where objects have x and y components, break it down and only look at x or only look at y at a time. So set your initial x momentum equal to your final x momentum, set your initial y momentum equal to your final y momentum, and run through the equations that way. I've got a quick example of that. About football! It's game day. The quarterback has a mass of 113 kilograms, runs east at 4.5 meters per second, when a defensive tackle with a mass of 158 kilograms runs south at 3.8 meters per second. When the quarterback is tackled, both of them fall to the ground together. So this is a perfectly inelastic collision. They both move with the same velocity in the same direction at the end. So what is the speed and direction right after contact is made? Well, let me draw a little picture of what's going on beforehand. I've drawn the quarterback's vector in red and the tackle's vector in blue. The quarterback is running due east at 4.5 meters per second, and the tackle is running due south at 3.8 meters per second. They're going to collide here. And just after the collision, they're both going to be traveling southeast. And that'll be at some angle theta south of east. I know the initial x momentum has to be the same both before and after. Well, in this example, the only x momentum is coming from the quarterback. So that'll be 113 kilograms times 4.5 meters per second. Multiply that out. And this system had an initial x momentum of 508.5 kilogram meters per second. It means it has a final x momentum of 508.5 kilogram meters per second as well. Same thing in the y direction. The initial momentum in the y direction, provided only by the tackle, is going to be the same as the final momentum in the y direction. Since all my momentum is southward in the y direction, I'll call that positive so I don't have to worry about playing with any negative numbers. When I multiply the tackle's mass by his velocity, I end up with 600.4 kilogram meters per second, so that'll be the final momentum in the y direction. Looking back at my final momentum vector, I can use this x component and this y component and ultimately use the Pythagorean theorem to figure out the grand total momentum using these x and y components. And punching out the math for that, you end up with 786.8 kilogram meters per second. Now that's not what the question asked. It asked what is the speed and direction they travel just after contact is made. So I've got their momentum, and since they're latched together, this momentum will equal the sum of their masses times their final velocity. So all I've got to do is divide 786.8 by 113 plus 158. When I do that, I get around 2.9 meters per second. Now I need to figure out what theta is. Well, I've already got the x and y components. That's the opposite side, that's the adjacent side, so seems like a perfect time to use the tangent of theta. So, taking an arctan of 600.4 over 508.5, I end up with an angle of around 49.7 degrees south of east. And that's about it, all you gotta know for test 3. So take a look at last year's test. I've got the problems and solutions up on Canvas. Take a look at some sample problems that I've posted under the modules on Canvas. Take a look back at any old WebAssigns, and take a look back at any old notes you might have taken with in-class problems, and let me know what I can do to help you study any further. Good luck!